Hello everyone, welcome to our deep dive into working with image data in Python for deep learning tasks. I am Bhargavi. In this video, I'll walk you through the fundamental steps involved in preparing and processing image data. I will start by discussing the different types of images such as RGB and grayscale and explain about image dimensions. Next, I'll move from theory to practice by demonstrating how to handle and process image data using Python. You will see how to convert raw images into numerical formats that neural network can understand. I will also cover essential techniques and libraries that make this process effective. Now, let's understand the fundamental steps involved in preparing and processing image data. Training data. First, we need lots of images. Neural networks learn by looking at these images just like how we learn by seeing different objects. Next, direct input limitation. But we cannot give these images directly to the neural network. It can't understand them as we do. Necessary pre-processing. So we pre-process the images. This means we can make some changes like resizing and adjusting them so that the neural network can handle them better. In data conversion, we convert these images into numbers. Each pixel in the image gets a number that represents a color. This turns the image into a format that neural network can understand. As you see, in modern compatibility, finally the numbers are fed into the neural network. Now the neural network can analyze the data and recognize patterns, helping it understand what's inside the image. Let's look at image types. There are two important types of images. As you can see here, grayscale image and RGB image. Grayscale images are composed of shades of gray, ranging from black to white. Each pixel in a grayscale image has a value that represents the brightness or intensity of light. An image is also defined by its dimensions, height and width. Consider this image has 300 pixels in height and 150 pixels in width, making up a total of 45,000 pixels. In a grayscale image, each pixel has a value between 0 and 255. 0 represents black, whereas 255 represents white, and the values in between represents different shades of gray. Okay, now let's move on to RGB images. RGB stands for red, green and blue. These values ranges from 0 to 255, and by mixing these three colors in different proportions, we can create millions of different colors. Just like grayscale images, RGB images have height and width dimensions, but each pixel has three color values. The total data is three times that of a grayscale image. As grayscale image needs only one value per pixel, which we consider as one channel, while an RGB image needs three values per pixel. So we define it as three channels. This makes RGB images more detailed and colorful, but also larger in file size. With theory explained, let's walk through the code to see how we implement these concepts in practice. I will guide you step by step through the Python code, explaining each section, starting from importing libraries, loading image data, converting it to numerical format, and preparing it for deep learning tasks. Let's look at the code. First, we need to download an image from the internet. We will use the wget command for this. It's short for webget, and it allows us to fetch files from the web directly into our working environment. Here is how we do it. I searched for cat images in Google and I copied the image address and then I gave this URL as an input to the wget command. This command allows us to download the image directly to our current directory. As you can see, now that our image is downloaded, let's read it and convert it into a NumPy array. We are going to use three libraries for the image processing: matplotlib.image, Pillow library, and OpenCV library. Matplotlib is a powerful library for creating graphs and plots, and it includes a module specifically for handling images. Now let's talk about Pillow and OpenCV. Pillow library is widely used library for image processing tasks, and OpenCV, which stands for Open Source Computer Vision, is a powerful tool for computer vision tasks. First, let's import the necessary libraries. We will start with matplotlib.image as mpimg. This convention is widely used and helps us keep our code clean and consistent. Now here, as you can see, we have imported this library, and we also import matplotlib.pyplot as plt, which is helpful for displaying images. Now let's load the image using matplotlib image module. I created variable name img and used the imread function from mpimg to read the image. As you can see here, I gave input to this imread function. As you can see, this is the image we downloaded from the internet, and as you go here, you can see copy path. Copy this path and give this path as an input to the imread function. Now this image is read and stored in the variable img. Now we use the type function. This will tell us about the data type of the variable img. As you can see, the image has been loaded as a NumPy n-dimensional array. Next, let's check the shape of the image using im.shape. Gives us the shape of the image. As you can see, the first two values represents the height and width, and the third value represents the color channels. Since this is an RGB image, we have three channels: red, green and blue. You can think of this particular NumPy array as three matrices, each of shape 463 and 703, representing the three color channels. All the values in this array here, as you can see, all the values in this array are between 0 and 255, where 0 means black and 255 means white. But it's not just about converting image data to a NumPy array. We can also convert this NumPy array back to an image. Let's see how we can do this reverse step. These back operations are very useful in image recognition and computer vision tasks. As you can see, displaying the image from NumPy array. Let's see how we can do this reverse step. Here I created another variable called img plot and set it equal to plot.imshow. This command shows the image represented by the NumPy array. Finally, plt.show converts the NumPy array back to an image and displays it. And here it is. As you can see, the x-axis and y-axis represents the pixel numbers. Simple yet powerful tool to work with images in Python. Now let's talk about Another important step in preparing images for neural networks. Resizing images. First, let's understand why resizing is important. Imagine you have a dataset with 10,000 images. For a neural network to process these images correctly, they all need to be the same size. If the images have different dimensions, it can confuse the neural network. So we need to resize all the images to a common dimension. Further, we are going to use the pillow library. In here, PIL stands for a short form of Python Imaging Library, and image is the module within this library. Here I created a variable img and used image.open to open the image file. I resized this image from its original dimensions of 463,703 to 200,200 pixels. Using the resize function, we resize the image to 200 cross 200 pixels. Then we save the resized image using the save function, specifying the new file name. Let's visualize the resized image using the matplotlib library. I used mpimg.imread to load the resized image and plt.imshow to display it. As you can see, the dimensions are now 200 cross 200 pixels with both x-axis and y-axis reflecting these values. Let's check the shape of the resized image using the shape attribute. As you can see here, the output confirms that the image dimensions are indeed 200 and 200 pixels. You can resize your images to any dimension you need. As you have seen it, we have walked through resizing images using the pillow library, saving them and visualizing them with matplotlib. Now we are going to learn about how to convert an RGB image or color image into a grayscale image using OpenCV. Here I took our original image and used an OpenCV function to convert it to grayscale. I started by using the cv2.imread function to read the image file. To check the image type, we use the type function. This confirms that the image is read as a NumPy n-dimensional array. As you can see, the image is loaded as NumPy n-dimensional array. Now let's check the shape of the image. I use the img.shape and the shape of the image is 463,703 with 3, indicating that this is an RGB image with 3 color channels. Next, I converted this RGB image into a grayscale image. I used the cv2.cvtcolor function from the OpenCV library. This cv2.cvtcolor function is used to convert an image from one color space to another. Here we are converting from RGB to grayscale. The inputs for this function are img variable. This is our original image that we want to convert. This image is assumed to be loaded in RGB format, and next the input is cv2.color_RGB to gray. This is a flag that tells OpenCV to convert this image from RGB to grayscale. Now let's check the type of the grayscale image. As you can see, it's numpy.n-dimensional array. Then let's check the shape of the grayscale image variable. As you can see here, there are only two inputs, 463 and 703. As you can see previously, it's 463, 703, 3. It is an RGB image, so we have three channels. Now the image is converted from RGB to grayscale, so there is only one channel, and so it is showing only height and width as inputs. So now with this we can confirm that our image is converted from RGB, that is color image, to grayscale image, that is black and white image. Next, I want to display the grayscale image. Since I was working in Google Colab environment, I use the cv2 underscore I am show function from google.colab.patches. As you can see, the image was converted from RGB to grayscale. After that, I saved the grayscale image using the cv2.imwrite function. This function saved the grayscale image under the name cat underscore grayscale dot underscore image. Now let me explain why we converted RGB image to grayscale image. Converting to grayscale saves a lot of space. Instead of giving three matrices, one for each channel, we only have one matrix. This reduces the computational power and processing time. However, you can't always convert images to grayscale. In some cases, the color information is crucial. For instance, in autonomous vehicles, recognizing traffic lights and road signs relies heavily on color. A traffic light's color indicates the vehicle whether to stop, go, or yield, which is essential for safe driving. On the other hand, tasks like detecting lane boundaries or obstacles can be done using grayscale images since the shapes and contrasts are more important than the color. I hope you understood the video. Thank you.